everybody. Thank you for joining again. Today is the second part of my lecture on remediation design. And I introduce myself again in case you missed it last time. Professor Tom Boving. I'm a Fulbright scholar at the IIT Roorkee, and I am tasked to give you a few lectures on remediation technologies that I'm an expert in. Now, if you remember, last time we talked about conceptual site models. And conceptual site models, or short CSM, is an integral part of the polluted site investigation process. In fact, a CSM can be an effective communication tool to explain non-technical persons what the remediation or the site investigation is all about, like seen in this picture here, where complex spatial issues like where are the tanks buried or where are the contaminants residing can be explained to people who may not have the background in remediation engineering. Also, it helps, CSM helps in planning a site remediation. And in fact, I would say CSM is essential to ensure that we can achieve the site remediation within the cost framework that's given to us and within the time framework given to us. And failing to have a solid CSM can actually lead to failure to achieve the remediation goals. So in all, a CSM, a conceptual site model, is essential for the engineering process when it comes to remediating sites. And here were the elements that led to not just the CSM, but also to the remediation of a project, starting with defining the project objectives, leading to hopefully remedy project completion. So there is flexibility required in the engineering process of coming up with a CSM and ultimately leading to the remedy process. And this is the topic of today's lecture, where we're focusing basically on this upper box here, the remedy optimization and completion process. And in particular, here we're talking about the adaptive design. So principles of adaptive design. The design process is a common thread through all engineering disciplines. It is usually a linear process where we start with asking the question, what needs to get done, and ultimately how we get there. Now, in adaptive design, we're following a more circular and iterative process, meaning we're still asking the question, what needs to get done, but we're arriving at the solution through iteration in a circular process. Now, for remediation engineering in particular, this process has 6 elements. It starts with defining the problem. What do we need to do? Brainstorming, how we get there. Planning, testing, refining, and if needed, repeat the process. And ultimately, we want to get to the point where we can deploy our remediation strategy. So in the next few slides, I will go over all these elements one by one and give a little bit more insights into what each element is and what it's about. Let's start with definition. The defining first step is to articulate the remediation requirements. By that I mean, what does a system must to achieve and which features does it must have to meet the objectives? That also includes performance specifications. What must be measured to measure success or failure of a design? Success and failure are very close to each other. We need to know when we can claim success, but we also need to know when to admit failure. And this is part of the performance specification process that defines our project. Also, we need to define remediation constraints. That includes cost, the size and footprint of our operation, the limitations, the degree of visibility or disruption to other site operations. Okay, so let's again go over these issues one by one, starting with the remediation requirements. And by this I mean the requirements mean we have to meet and satisfy requirements imposed to us either by environmental laws or by the applicable environmental permits. strict environmental laws are in place for a reason. They need to be followed and they are enforced. And the permit, environmental permit, is what makes our project possible in the first place. So we must ensure that we follow the environmental law and any applicable environmental permits. It also means that we have to be cognizant and follow orders and directives of government authorities, and also be cognizant and follow the instructions given by settlement agreements, which usually happen between a lawyer and a site owner or and the government, seeking settlements in terms of cost and responsibility for installing and cleaning up a site. And this, of course, has to do with the release of hazardous substances. So we must also know about the nature of hazardous substances and their potential implications for the health of the environment and the people. Now, in terms of performance specifications, this means we have to have a structured program in place to measure the success at every step of our investigation and also of the remediation of a polluted site. So such a program must at minimum include a description of the status quo. So what is the baseline? What are we starting out from? What are the conditions before we implement our remedy strategy? That means we have to have a summary of historical investigations, meaning who owned the site when, what was being done on the site, what kind of processes, what kind of chemicals were used, where have they been used, and so on. It's a long and complicated process, has something to do with detective work often, because one has to go through reams of reports and often includes interviews with people who worked at the site for many years. Sometimes these people are already retired, so it requires to identifying and finding these people and then talk to them, gather all the information that gives insights about the historical use of the site, because when we understand the historical use, we can then deduct what kind of processes happen and where are the potential problem areas. So we want to identify pollution sources, but we also want to identify endangered natural resources. What are the surroundings look like? Is there, for example, a drinking water treatment plant in the neighborhood? Is there any facility that could be impacted through the contamination that's being released at the site? How long would it take for this contamination to reach there? Now, that means we have to have clear objectives of our technical investigations, plural, and we need to have clear milestones that take us from one step to the next. And with any project, we need to have a full documentation of the investigation program and the quality assurance and quality control, or short QA/QC procedures. QA/QC procedures are essential because it holds up the standard to which we agree to apply and which everybody involved in the project has to be aware of. And when these quality assurance and quality procedures are followed, then the success of the project is very likely. Otherwise, it can lead to failure, as I mentioned earlier. So when it comes to remediation constraints, there are many that we need to be aware of because, again, we need to plan for these constraints and find solutions before we start a project. So, for example, remediation of large sites with multiple source zones and overlapping plumes is a very costly undertaking. There are many examples all around the world where sites have been remediated for many years, for decades, for several decades, and accumulating costs that are in the tens of millions of dollars. And these sites are not even done yet. So this is definitely a constraint, knowing the cost and the time it may take to remediate a site. And that leads to the next question. Who is the responsible party, or parties, plural? And who's paying for what? Again, we're not talking small sums of money, so it needs to be clear who's paying for what. And often, as it is in the case of the United States, when there's no responsible party to be held accountable, it falls back to the taxpayer. And when the taxpayer is involved in cleaning up these expensive sites, the taxpayer wants to know that the tax dollars are spent appropriately. Another constraint to consider is when you install remediation equipment, it can be large. It can include wells, pipes, towers of activated carbon, towers where water is being stripped from volatile organic contaminants, and so on and so on. These are huge pieces of equipment that can impact the sites, not just in terms of use, because these pieces of equipment take on large areas, but they can also pose disruptions to the operations of an industrial site. Often these are factories that are still very much active, producing whatever you want, and having these big pieces of remediation equipment sitting on the site can block access or can pose restrictions on what can be done on the site. These are concerns that are very important for the operator of the site, because they need to adjust their operating procedures to accommodate you, or vice versa, which is more often the case than not. Also, there are the issues of visibility. Not every remediation site owner or the responsible parties wants to advertise that there is something going on their site, like a remediation. So big pieces of equipment that are clearly related to, let's say, water treatment could be seen as something that the site owner doesn't want to be public, and therefore it requires you, the remediation specialist, to find a solution how to address those concerns. And then ultimately another concern is the carbon footprint of your operation. This becomes more and more, this gets into the foreground more and more these days, because during many years, decades of operation, the amount of carbon released is tremendous in some places. So we need to know how much fossil fuels are being consumed in the remedy process, and how is that in relation to the goal that we're trying to achieve, bringing back the site to good use. So if we're burning much more fossil fuels than are being extracted from the ground, the question can be asked, is it worth it from the environmental point of view? And this is a question that definitely needs more research, and that's what is very much on the forefront of many people's minds right now. So together, the remediation constraints can have a severe impact on our planning process. And we're still only in phase one in the defining the problem. Now, moving forward, taking all these bits and pieces of information together is clearly showing that this is a complex undertaking. It's much too large of a problem for one person to address. So it is basically requiring the input of a team. And the team should have a leader, and the leader should encourage creativity and avoid immediate dismissal of ideas. Meaning, we want to have a lot of people on the table, and these people can be from a multitude of fields, such as research, hydrogeologists, and geologists, engineers, chemists, microbiologists, public health professionals, ecologists, and also lawyers and bankers, because the lawyers and bankers have to bankroll the undertaking and also have to ensure the legality of what is being planned. So it's not just researchers and engineers, but a whole lot of people with different backgrounds coming together to answer or brainstorm on the development of the site remedy. And that's what's so fascinating about remediation engineering. It is really a multidisciplinary undertaking, and remediation engineering draws, like I mentioned in the previous slide, from all these various disciplines and subdisciplines. And again, it is so complex that we just have to work as a team using all these multiple disciplines available to us. All right. So after brainstorming follows planning. And designers, engineers tend to divide a problem into individual pieces and then test these pieces at different steps. So the the available information is synthesized into a plan for implementation. It starts with conceptualization design, about what we call it 30% design, or the configuration design, 60% design, which leads to the detailed or 90% design stage. So again, it's a stepwise process that is clearly defined and has certain milestones that need to be met in order to move on to the next phase. Also, very important, there's never one right way to answer a given problem. So at the conceptual stage, or the 30% design stage, there still may be several alternatives on the table, and we still in the process of selecting which one of these designs may be correct for us, and maybe it's a mix of designs that need to be considered for the project. So at this stage, very much everything is still on the table, but when we follow along with the process and eventually get to the 90% stage, we should have eliminated those processes or techniques that do not meet our process design criteria. And at the detail stage, we should only be left with one or maybe two or very few uncertainties that need to be addressed still. Then we move on to the actual testing, to the implementation, the testing stage. And at this stage, it is still about collecting proof of concept information and also physical information that supports our implementation part. That may include laboratory tests, like testing salt contamination, what type, confirm which are the contaminants, where are they, and so on and so on. And laboratory testing usually goes hand in hand with field testing. This may be also including prototyping, new technologies that are still in research that need to be prototyped before they can be scaled up. It may include numerical modeling and more so these days, the artificial analysis of complex data sets. Just the two examples I want to give you of what this may imply. So for example, if the considered remedy for a plume that is approaching, let's say, a drinking water well is hydraulic control, then we have to have certain understanding of the site before we can implement hydraulic control. So hydraulic control briefly is installing a well right here in the path of an advancing plume. The plume in this drawing is shown in blue, right? So all the blue area means it's contaminated water. And we want to ensure that that plume, that contaminated water, is not passing a certain point. And that not passing the certain point includes the installation of a well, an interceptor well, or how we call it, a hydraulic control well. So this well is designed to capture all the polluted water, pump it out of the ground, ensuring it doesn't get any farther than that. So as you can see, this is a fairly complex undertaking because we need to know where to put the plume in relation, where we want to put the well in relation to the plume. We need to know how much water we need to pump. Therefore, we need to know a lot of parameters of the site that are not readily available usually. So this requires testing in the field and possible modeling exercises. Just to give you an idea of some of these test parameters that we need to find out from our field testing, it includes measuring hydraulic conductivity, which hydrogeologists know is a very important quality of the soil and the liquid, the transmissivity of the aquifer, how much water can be moved through a given cross-sectional area. We need to know the hydraulic gradient, that's the steepness of the water table, which tells us about the velocity by which the groundwater moves, and many other things. We also need to know the well yield, how much water can be pumped. That determines, for example, the size of the pump. Does it have to be a 5 horsepower pump, 10 horsepower pump? Does it need 220 volt? Whatever. It gets technical very quickly. And also, ultimately, I should say, we need to know the capture zone, which is determined by all these other parameters that I mentioned, hydraulic conductivity, transmissivity, and so on. And the capture zone is what really determines the success or failure of hydraulic control. So in other words, what seems to be a pretty straightforward solution to a problem can quickly turn into a massive amount of data that needs to be first researched and determined, and this again requires field lab, laboratory, and modeling exercises. Another example is bioremediation. Bioremediation, a popular remediation strategy, is a process of detoxifying or degrading contaminants that are present in the soil or wastewater or industrial sludges using biological means. That means we let bacteria, fungi, or other microbes loose and have them eat, destroy the pollutant and turn it into a benign product. However, before implementing a bioremediation scheme, one must determine first, are these microbes present at the site? Are those microbes that are present the right microbes? Do they finish the job? And then importantly, is their number, their concentration high enough? Meaning, will the bioremediation proceed in a speedy manner that we can achieve our remediation goals in a reasonable amount of time? So again, we need to go to the field, we have to collect samples, we need to do research, microbiologists become involved, counting the bacteria, identifying the bacteria. All this goes together in the pre-designed testing that leads us eventually to an optimized remediation system, which gets us to the next step, and that's the refine stage. So all these prior processes I just talked about still have uncertainties regarding performance, reliability, and also safety. And these uncertainties need to be minimized to the greatest extent possible. That means we have to redefine the elements of our adaptive design strategy and go back maybe to the planning board and say, okay, admit failure, this particular process we had in mind didn't work or will not work. We need to have a different solution or maybe a modification. So different alternatives have to be redefined until ultimately the design is optimized to a degree that it's both acceptable and most effective possible process. And when this is all done, we finally arrived at the stage where we can deploy our remediation process. And again, it's not a straightforward process. It involves steps. First of all, the construction of our necessary equipment, drilling wells, setting up equipment as needed. And that includes quality management, ensuring that all pieces are of the desired quality to manufacturer specifications or beyond, and ensuring that all elements are being connected appropriately, the plumbing, the electricity, many, many issues here. So once we have constructed our system, we need to undertake operational testing and evaluation, or typically referred to as system shakedown, meaning we have to ensure that all the elements of our remedy technology work as designed, work together as designed, and troubleshoot any processes that may fall outside their parameters, or let's say a pump is not sufficiently powerful, we need to replace it with a more powerful pump, and so on and so on. And accordingly, we have to undertake modifications based on the shakedown and ensure, again, iterative process that we end up with the system that we designed to, or we hope to design to meet the specific objectives of our plan. So when all this is done, hopefully we can go to the long-term operation, the monitoring and maintenance. And as I mentioned earlier in my lecture, we may be in for many, many years, maybe decades. So we have to keep in mind that operation, maintenance, and monitoring are long-term propositions. So we have to have people there that are trained, that know the system, that can fix problems, that can identify problems in the first place. And we need to have these operation procedures documented in great detail so we can ensure that everybody involved knows what to do, when to do it, and what actions to take if the system doesn't perform as designed. Okay, So this basically is the iterative or the adaptive design principle that I wanted to explain to you, but I can't stop without mentioning two more things, two more design issues that need to be part of an engineering design for remediation, and that is health and safety and environmental considerations. Now, health and safety in design is a very important element, often overlooked, but very important. In fact, it's probably the most important design, because if something can't be done safely, people say, it shouldn't be done at all. Nobody wants to get hurt. Nobody wants to get killed during a site cleanup. So it needs to, any design needs to be done so it's safe, and it needs to be done, it is environmentally friendly. Now, health and safety must be the first priority throughout the entire process, and that means integrating health and safety into the initial proposal, into an initial decision-making process, the project planning, project execution, and ultimately in the project closeout. So all along the entire process, we need to be aware and cognizant about health and safety. Now, a health and safety plan is typically required for each project, and it has like three elements. First, hazard identification and critical failure analysis. So what are the contaminants and what can go wrong? And that's not just the contaminants, but also what can go wrong during the remediation technology, during the operating of the many parts of the system, the wells, the pumps, the electrical equipment. All these system parts have to undergo a critical failure analysis. And then a hierarchy of hazard controls have to be developed. Engineering controls, work practices and administrative controls, and also the availability of personal protective equipment, or short PPE. So all that needs to be addressed in the health and safety plan. And then ultimately, 3 is the response planning. So what if, after all this planning, after all the precautions taken, something happens? How do we respond? Where's the next hospital? How do we reach the next hospital? How do we call the firefighters? How do we call the hazmat people? All that information has to be part of a health and safety plan, because we know we're all human. Things go wrong. We need to be prepared. And that's really the concern or the main drift of a health and safety plan. And these plans can be extremely long. I've written a few myself, or helped writing them. And 100, 200 pages of information is not uncommon, because there are so many considerations from the beginning of the project through its duration to the closeout, which have health and safety concerns which need to be addressed before the project even starts. Now, the last part of the design process I want to talk about is how we address environmental considerations. Again, our business is to clean up polluted sites. That's for first and foremost what we want to do. But during the process, we have to ensure that our actions do not have negative environmental consequences to the area surrounding our active site. So we have to ensure, for example, that volatile emissions and odors do not are not released from our site and bother people in the neighborhood. It's very quickly that people neighboring a remediation facility will call the police and complain about odors. I've seen this myself. It's not a good place to be in, because then the police and the environmental regulators show up and say, hey guys, something is stinking, cut it off. And that means you have to probably shut down your operation, at least until you find a solution to minimize emissions and odors. Same is true for dust particles, dust and particulate emissions. Either during the construction, during the investigation, during the construction of the site, and also during the regular monitoring and maintenance procedures, you have to control dust and particles, because these particles are a nuisance and in fact can endanger the health and safety of the people living in the neighborhood. Noise, obviously, right? Who wants to have trucks coming in and out every time of the day at nighttime? Could be an issue, has to be addressed. And vibration and subsidence. Vibration means when you operate heavy equipment, rumblings may cause cracks in buildings. If you extract groundwater during your remediation, it can lead to subsidence issues where the soil is shrinking, again putting strain and eventually leading to breakage of slabs of concrete or basements. All this has to be considered, because if it happens, it's usually not a good thing for the person in charge of the remedy. Traffic and security, these are issues during the construction, during the maintenance. There, again, heavy equipment involved. How do we ensure that the traffic is not impacted so people can go to work, come home from work, and so on. So security, obviously, to protect access to the site, ensure that only people with the proper training, with the proper personal protection equipment have access to the site and nobody else. And then ultimately, protection of the surface water, lakes, stormwater runoff. In this picture, for example, you see berms of hay and straw that is supposed to slow down the force of water, meaning the water and the particulates suspended in it needs to be captured and prevented from migrating off-site. Because again, these soils can be polluted, and the last thing you want is polluted sediments washed off during heavy rainstorms onto neighbors' property. That is a big problem. So these are some of the environmental considerations. Again, each site is unique. Each site needs to have a specific environmental health and safety plan, for the people as well as for the environment. And all that, as I mentioned earlier, has to be documented in great detail, because A, we want to ensure that our planning is transparent, it's understandable, and also we want to identify mistakes when they have been made. So without proper documentation, we may not be able to identify where, when a failure or a mistake happened, and we will have a much harder time to address that mistake if we don't know the process that led to it. So documentation is a big, big issue. And like I said, health and safety plans are always site-specific, so it's not a cookie cutter cut and paste, but we need to know what are the particular conditions at a site and how do we address them in our reporting. Well, as you can see, this is a very complex process. It's adaptive, it requires flexibility from the engineer, requires flexibility from all the many people involved in the planning. And it's a process that's designed to learn from mistakes, to adapt to problems, to be iterative until a final solution has been found that satisfies the project requirements. And again, this is something that is true for all engineering disciplines. If we don't have a plan in place, we're probably not going to get to where we want to be. And it's a team effort, and it's a process that requires considerations of health and safety as well as environmental considerations. And with that, I'd like to thank you for your patience and hope you have a good day. Goodbye.